Okay, this is lesson 10, and we're going to start with a review of lesson 9. If you remember, we went through looking at a resistor circuit, a capacitor circuit, and an inductor circuit, and we figured out how the current and voltage were related to each other, and we've found some equations for those. So on page 81, I have a place for you to write all of this, and I have already started with it on the board. So for the resistor, this would be the phasor diagram. The current and voltage are along the same line. For the capacitor, if you remember that in lesson 9, we had the voltage in the first quadrant and the current relative to it, 90 degrees, supposed to be 90 degrees. And then the inductor, we still left the voltage in the first quadrant and the current was down here in the fourth quadrant. Again, these are 90 degrees apart. So then in the second line, or the next line, we have a place for you to put the voltage as a function of time. And all of these look the same, except they have a different maximum. This is the resistor maximum, capacitor maximum voltage, and inductor maximum voltage. And then the next line is the current, and from here you can see that the current and voltage are in the same quadrant, so they should have the same expression. In this one, the current is different than the voltage, so we have to add pi over 2 here to get the proper equation for the current. And then for the inductor, the current is down here, so we had to have minus pi over 2. So we have those. Now I'm not going to write the next two lines. The current maximum is the voltage maximum divided by the resistance. So it will be divided by R here. It would be divided by XC, which is the reactance. And for this one, it would be divided by XL, which is the reactance. And then in the last row, I have a place for you to put resistance or reactance. Resistance is just R. Reactance for the capacitor is 1 over omega C, and the reactance for the inductor is omega times L. And I'm not writing those up here because I'm going to use this space for what we're going to do on the next page. So it says to draw a series RLC circuit, and I will do that in a very small space right here. So we have an alternating voltage source, and it doesn't really matter which one you draw first. So I'm going to put the resistor and then the inductor and then the capacitor and then back to here. So this is resistor, inductor. Make sure those lines are the same length, and that's a capacitor. Remember that in series, the current is the same at all points at any particular instant. And that's actually a major point of what we're going to do next. So if we look at the three circuits, or the three phasor diagrams, the currents are not pointing in the same direction. So we just said that in a series circuit, at any particular instant, if you had an ammeter that would measure the exact current, it would give you the same value. Now again, the current is alternating, so it's constantly changing, but at any particular instant, the current is the same at all points in this circuit. So with that in mind, we're going to look at these three phasor diagrams and sets of equations and modify them so that we do have the current the same for all three of those. Now, for the resistor, this is going to stay just like it is. So on page 82, the phasor diagram for the resistor will be this, and the voltage and the current will be what we had on the previous page. Now, when we get to the capacitor, in order to make the current the same at all points in the circuit, at any particular instant, we have to have the current vector in the first quadrant like this way. Now, when we derived this, there was no real reason to rotate or shift anything. It was very easy to start with this voltage, and we ended up with this equation for the current. But now what we want to do is to rotate this phasor diagram. So this is what you should have in the phasor diagram capacitor box, and this is on page 82. So what I'm going to end up doing is drawing the new phasor diagram here, and then I'm going to modify these two equations. So the new equations that we get here will be what you need to put on page 82. But let's first figure out what we need to do in our phasor diagram. So what we need is the current needs to be in quadrant 1. So we're going to rotate this diagram so that we have current up here. This is going to be IC max. Now there's nothing that says that this phasor has to be in that position. What does have to happen though is the voltage vector must stay in the same position relative to the current. So if I've rotated this around and I put the current out here in quadrant 1, then VC has to be down here in quadrant 4. And I'm going to see if I can get it a little bit more perpendicular. That looks like it is perpendicular. So this is going to be VC max. So notice that it looks the same, except we took this one up here and rotated it to this. Now, if we're doing that, then we have to modify our equations here. So in order to help you keep track of which equations go with which phasor diagram, as I modify these, I'm going to draw them or write them in red to match this picture. Okay, so what we need is the equation for current needs to be the same as our equation for, the current for the capacitor needs to be the same as the current for the resistor. So what we need to do is to not have this pi over 2 here. But we can't just erase it. We have to do something. We have to modify the voltage equation so that it has the same relativeness to the current. So if you think about this, this one is plus 0, this is plus pi over 2. Let's subtract a pi over 2 here, and then we have to subtract a pi over 2 up there. So what we're going to end up with for these sine terms, you'll still have this first part the same, but we need up here to have sine of omega t minus pi over 2, and then this is just sine of omega t. So this should be the voltage equation as a function of time across the capacitor. This will be the current equation as a function of time across the capacitor. So we have the same form for the current for the capacitor as we have for the current for the resistor. And we have kept the same, these are relative, still relative to each other the same way that they were. This one is still pi over 2 more than this one. So if you add pi over 2 to this, you end up with nothing there, which is what we have there. I'm going to put this in parentheses. Okay. So that fixed our capacitor problem. Now we need to go to the inductor problem. So on this one, we have the current in quadrant 4. It needs to be rotated back up into quadrant 1. So we're going to have that phasor diagram with our current up in quadrant 1. So it's something like that, IL max. And then the voltage vector is still 90 degrees from that counterclockwise. So it must go out this direction, and this will be VL max. And that's at 90 degrees there. So these two diagrams, actually this one is down here as well. I'm not going to redraw it. So this diagram, this one, and this one are what you should have in the row for phasor diagram on page 82. And then these two equations stay the same for the voltage and current. And then these two, now that I have in red and black, these are what you have for the voltage and current for the capacitor. Now we need to modify the ones for the inductor. So the one for the current for the inductor must have just sine omega t. And then that equation will be the same as what we have for the capacitor and the resistor. That tells us that the current is the same at all points in the circuit at any particular instant. Now, we have to modify our voltage equation to keep it the same relative, or relative to the current. So we had minus pi over 2 here. So we added pi over 2 to get nothing. So now we need to add pi over 2 up here. So we have sine of omega t plus pi over 2. Okay, so these two equations are the equations for current and for voltage for the inductor. And so then we have our phasor diagram. So we can check again, our current equations are all the same. Now they still have a different amplitude out here, but they are still have the same phase. They're all just sine of omega. For the voltage, we have the sine of omega t, and here it's omega t minus pi over 2. On the inductor, it's omega t plus pi over 2. Well, what do we do with this? We still need to put these three things together into one picture, equation, problem, whatever you want to call it. So on page 83, step number 4, it talks about that we have these three phasor diagrams. So we want to put them together into a single phasor diagram. So I'm going to erase these, and then we're going to look at how we put those together into one phasor. Let me get rid of all of this. So what we're going to do is start with a big set of axes, and we're going to draw the voltage across the resistor. Now, since the current, the equation for the current was the same for all of them, we're going to draw this on here just to show that it's in phase with the voltage across the resistor. But the voltages are what we're actually going to look at. So I'm going to put VR max. I'm going to extend this to show the current. And since the current is the same at all points, now we don't need a subscript for resistor, capacitor, or inductor because it's the same. Now, I guess I could have left these up here, but if you look at the capacitor voltage was down in quadrant 3. So we're going to draw a vector down here. Now, we don't have values for these, but I'm going to draw it in a particular way to sort of illustrate kind of what we need to do. The homework problems that I have for you to do when you do the calculations, then you will actually end up plotting those to scale, or drawing those to scale. But here, let's just assume, let's see, how did I do this? Let's draw this one a little bit longer. And this is going to be the voltage across the capacitor maximum. And then the voltage across the inductor was up in the second quadrant. So it's supposed to be up here. I'm going to draw a rather long one. So this is voltage max across the inductor. Okay. Now, we have three vectors that we're interested in, VR, VC, and VL. And usually if you have vectors, what you want to do is to do vector addition. There are some complicated ways, and then there are some simpler ways. We're going to choose a simpler way, and we'll see why we're going to do it that way. Okay, so if we have VL in this direction and VC in this direction, we could think of moving, remember you add vectors head to tail. So we're going to move the VC vector from here up to here so that it's starting at the end of VL and coming back down this direction. That's supposed to be the same length as that, so I will just assume that it is. That's VC max. Okay, so if we have a vector up this direction and then another one back along that same line, then we have a region right here that's VL minus VC. Now, you might say, I thought we were adding. And it's like, well, yes. But knowing where we're going with this and what values we're going to be using, it's going to work best if we label this. Actually, these are maximum values. It's going to work best if we label this VL max minus VC max. Okay? So we have added the vectors along this line, and then we want to add that to our voltage vector across the resistor. And so I'm just going to use green anyway. The blue marker doesn't seem to erase very well, so I'm not going to use it. So we have this. We're going to draw a line out here and come up here, make a rectangle sort of out of that. Then from the origin up to that diagonal side, this is the vector sum of those. So it is actually the max of the circuit. And then the other thing that we're going to look at is this angle from the resistor voltage vector to V max, and we're going to call that the Greek letter phi, and that's called the phase angle. So it shows us how the maximum voltage vector is, or how it's related to the voltage across the resistor, and actually related to the current, whether it's in phase or out of phase or a little bit in or out. Now, we're going to actually do some calculations with all of this, and let's see, what do we do next? Okay, I'm not going to write out all of this. I think you're capable of doing this, but just sort of to point out what you do, this Vmax is the hypotenuse of the triangle. So one side is VR max, and the other side is VL max minus VC max. So we have this side squared plus VR squared, and then the square root of the whole thing, because that's the Pythagorean theorem. The square root of the sum of the squares of the sides. The other thing that you'll want to do is to write Vmax. Vmax is Imax times either resistance or a reactance. So for VR max, you will have Imax times R. If you have VL max, you will have Imax times XL. If you have VC max, you'll have I times XC max, or XC. So if you put all of that in and factor out the currents and divide both sides and do all of that, you should end up with a thing called the impedance, and that is R squared plus XL minus XC squared square root. So you want to make sure when you're doing this, it's not XL squared minus XC squared. You have to take the difference first. Notice that this is the difference. So that squared plus the VR squared will give you the hypotenuse squared. So you take the square root of it. Now, impedance is similar to resistance, except it can't be called resistance because it has to do with actual resistance of a resistor and the reactance of the inductor and the capacitor. And of course, these both depend on the frequency. So that's why it's not just called resistance. Okay, now the next thing is part 3 on the phase angle. So we can look at that briefly. We have the phase angle here, and we know the sides. This side over here is the difference of the voltages. This side here is the voltage of the resistor. And we can write that. Oh, let's go back to red. So tangent of phi is VL minus VC over VR. And these are all maximum values. You can use the same idea that voltage is current times resistance and factor out and simplify things. And eventually you should end up with the phase angle is the inverse tangent of XL minus XC over R. And you need to make sure that it is the L minus the C. If you do it the other way, then I guess it wouldn't matter in here, but it will, you'll get the wrong phase angle. Now we have one more thing that we'll look at briefly. This has to do with power. And we know that power is current times voltage. It's also I squared R if we have a resistor. So we're going to look at a general equation for power for a resistor. This is I squared R. Now, our current, though, is alternating. So we know the current is I max times sine of omega t. That whole thing gets squared times R. Actually, I realized I said just a minute ago that power is I squared R or X or the XL or XC. The power does not have anything to do with the inductor or the capacitor. Power is only related to the resistance, and that's actually an important feature that we're going to look at in just a minute. Now, we can rearrange this a little bit and put I max squared times R, and then we're going to put sine squared omega t. So again, our power depends on sine squared. And since this oscillates, then obviously sine squared will oscillate. So power varies, and that's not very useful. So what we want to do is to look at an average value, and an average value of sine squared is 1/2. And if you've done some math and calculus before, that's kind of a standard thing that they do in calculus classes. You don't really need to know how to do that, you just need to know that that's what it is. So if we're looking at average, so P average, and I'm sort of in step 2 now at the bottom of page 84. So P average, if you look at the average of sine squared, you're going to get 1/2. Then we have I max squared times R. And that would be okay, but we want to do a couple of other things with this. So what we do is put I max, and then I want to get this 2 in here, but it needs to go so that I can put a squared. So I want I max divided by something, and then have that whole quantity squared. So after it's squared, it has to be 2, so before that, it must be a square root of 2. And then this is times R. Now if you go back to looking at the definition of RMS values for a sine wave, this term in here is an RMS value. So our average power becomes I RMS squared times R. Okay? Now, we can also write this in terms of voltage. So we can separate this as I RMS times I RMS times R. So current times resistance is actually voltage. So this then becomes I RMS times voltage RMS, so our average power. And you might be thinking, well, yes, but why do we need to do that? Where are we headed with this? Well, where we're actually headed is if we look back at the phasor diagram. So I'll just draw a little one up here. We had VR there, we had VL up here, VL, we had VC here, and then if we add this one, we get this back to here. So this part here was VL minus VC, and then we do this thing here. This is V max, and here's our phase angle. So it's probably going to be better if you look back at the one that you drew on the top of page 83. So if we look at that and look at the phase angle, we can see that the cosine of the phase angle is VR over V max. So VR max. Well, it turns out that if we have a ratio of maximum values, if we converted them both to RMS values, we would have the same ratio. So the cosine of phi can be written as VR RMS over V RMS. Okay. Then we can solve this. The R RMS is V RMS cosine of phi. And then we can put that together, put that back into here. We can substitute, okay, hold on. This I times R is the voltage across the resistor. So this should be R, voltage across the resistor, RMS. Okay. Now then, we can substitute the voltage, the whole voltage RMS times cosine of phi in for this, and we will get, and I think I'll write it in red because that's an important equation. Where's my red marker here? So then we end up with P average is equal to I RMS times V RMS times cosine of phi. So that's our average power in terms of the current and voltage RMS of the circuit, then times the cosine of the phase angle. And this cosine theta, the whole cosine theta, is called the power factor. This equation is power, and then this is the power factor. So I think that's the end of the lecture part. This is going to be important in the next lesson because we're going to look at phi and try to decide what kind of phis do we want in our circuits and how do we get those. So this is the end of this part. There's another part that will deal with the experiment.